Section 13.11. Estimating the period. If you are a crypto hobbyist, you may want to try designing your own pseudo-random generator. This book will not cover how to test a PRNG, which is a big subject, but let's look at how you can estimate the period of your generator. The method depends on the size of the state vector. Section 13.2. If the state vector is small, say 31 bits, you can just run your generator for 2 to the power 31 cycles and see when it repeats. Unfortunately, it is possible that the initial seed will never repeat. There is a trick to handle that possibility. Make 2 copies of your PRNG and initialize them with the same seed, S. Then run the first copy 1 step at a time and run the second copy 2 steps at a time. Suppose you find after 3000 cycles that the 2 copies produce the same state vector. That means R3000 equals R6000, so the period of your generator is 3000, at least with the seed S. If the state vector is larger, say 64 bits, it is not feasible to run your generator for potentially 2 to the power 64 cycles. You can still estimate the period by using sampling. Make a table of, say, T equals 1 million entries. Entry n in this table will hold the number of the cycle when your generator produces the value n. Initially, set all of the entries in this table to 0, since no values have been produced yet. Choose a seed in the range 1 to t-1 and run your generator for perhaps G equals 1 billion cycles. On each cycle, if the value n that is produced is less than t, you record the cycle number in table entry n. If the entry is not 0, then you have a repeat, and that tells you the period. For example, if the value 12795 was produced on cycle 33,000 and again on cycle 73,500, then the period of your generator for that seed is 73,500 minus 33,000 equals 40,500. If you do not find any repeats, then you can estimate the period by seeing how many of the t values were produced. If e entries in the table are non-zero, then the portion of entries that are produced is e over t. Since you ran the generator for g cycles, the estimated period is g over brackets e over t equals gt over e. As we saw with the chained digit generator, section 4.5.1, a generator may have several different cycles, some long and some short. You should make several estimates for the period of your generator using different seeds. One good strategy is first to use seed 1. For the second seed, use the lowest value that was not generated by the first seed. For the third seed, use the lowest value that was not generated by the first or second seed. You can do this by making the table cumulative. Do not reset it to 0 between estimation runs. If the estimates for the period are consistent over, say, 20 to 100 such runs, then you can have confidence that your generator has a long period for most seeds. Section 13.12. Strengthening a generator. One method for strengthening a PRNG is using a selection generator that separates the operation of generating the numbers from the operation of selecting the numbers. This can be done by keeping n numbers in an array, say 32, 64, or 256 numbers. Each number in the array should be the size of the desired random outputs. For example, if you want to generate random bytes, the array should contain 8-bit numbers. The PRNG is first run for n cycles to produce the initial numbers, which are put into the array in the order that they are generated. Then the PRNG is restarted with a new seed. The generator is then used to produce a sequence of pseudo-random numbers in the range 1 to n. Each of these numbers is used to select an element of the array. This element becomes the next pseudo-random output. The selected array element then gets replaced by a new pseudo-random number using the PRNG. This means that the first, third, fifth random numbers are used for selection, while the second, fourth, sixth numbers are used to replace the numbers in the array. It may be convenient to use two separate copies of the PRNG with different seeds. However, this will not increase the period. A better strategy is to use two different generators whose periods are co-prime. Then the period of the combined generator is the product of their periods. For example, if the numbers are generated by a multiplicative congruential generator with period 2 to the power 31 minus 1, and the numbers are selected by a linear congruential generator with period 2 to the power 31, then the period of the combined generator is 2 to the power 62 minus 2 to the power 31, or 4.612 times 10 to the power 18. The period of 4.612 times 10 to the power 18 is long enough for cryptographic work, but the selection generator is still not cryptographically secure. This is because Emily can brute force the selector sequence and try all 231 possible seeds. With enough known plaintext, this could give her a sequence of outputs from the first generator, which would be enough to solve it. There are several possible remedies. 1. Use a combining function like XORs, adds or poly, which makes it hard for Emily to determine the random outputs. 2. Make the selector generator bigger, say 63 bits instead of 31 bits. 3. Make the seed for the selector generator bigger, for example by making the multiplier and or the additive constant part of the seed, namely m and c in the generating function xn plus 1 equals brackets m xn plus c, mod p. 4. Use the techniques in the following section to construct a selector with a longer period.